Hello guys, welcome to our lectures online. Okay, our extra classes online. We are going to look at electrical machines. In the last section, we looked at the voltages and the currents in a star connected systems, where we wanted to figure out the relationship between the phase voltage and the line voltages. So in that section, we discovered that the line voltage. So we were in a star connect system, and we did the derivation in that one, in those systems, and then we saw that we name in a star connected, we will name this one R, this one is Y, and this one is B. So it's R, Y, B. That is our sequence. And we say that here we'll be having an EMF which we call ER here, which is a what? An RMS value. This one we called EY. This one we called B, and this point here we called N. And then we said we'll have lines there. So this is our generator, and these lines are going to supply electricity. So we say now if we look at the voltage across these two lines, so because it's a voltage from Y to R, we call that EYR. And therefore, because it is the voltage between the lines, it is called a line voltage. And this voltage is between the neutral points, ER. And this is ER, we call these phase voltages. So we discovered that the line voltage was equal to √3 of the phase voltages. So this is simple to remember. If you look at this is line voltage, and we have a voltage where we are having two voltages adding each other there. Definitely, the line voltage must be bigger, okay? Kind of bigger anyway, in a sense. Okay, so that's what you would think here for you to remember this. So we discovered that this is what? The relationship between the line voltage and the phase voltage in a star connected system. And then we also say that the currents now in a star connected system, we say that these currents, if we have a current flowing there, let's say that's our phase current, we call this I phase. Then the current that is flowing in the outside line is called our line current. So if you start following this loop, you will see that it is this very same current that is flowing. So we realize that our line currents are actually equal to the phase currents. So line current is equal to the phase current in a star connected system. That's what we discovered the last time we looked at this. So today we'll be looking at the delta connected system. Then we see how this really is how different this system is. Okay, so now I'm going to look at a delta connected system. A delta connected system can be in form of a load, can be in form of a generator. So for a difference, I'm going to take it as in form of a load, a delta connected load. So in a delta connected load, we are going to have a load here. Delta connected loads, a load there, and a load here. Okay, so that this is our line, this is point R. So let me just label it here, point R there, and this one I label it point Y. Okay, This one becomes B, RYB. Okay. Now here you're going to see something that is very interesting. Okay. Now the currents, remember we said the currents flow in like a circular way. So I'm going to take this, let me call this is my load 1, load 1, and let me call this load 2, and this is going to be load 3. So the current coming from, we have a current now because this is a load. Remember, the load is being supplied by, we're going to give a current to that load. Okay, so we're going to have a line current flowing in that one. Let's call that line current IR. So when it flows in, and then we have another current here, I, Y. Then we have another current here, I, B. So I'm going to say this current flows in and then it goes into this load. So it becomes I1. Is this, okay? So that current flows here, becomes I1 since it's flowing in load 1. Now I1 is basically an RMS current that is flowing in the load. Remember, it's connected to a generator. A generator has changing currents, but we are going to take this as an RMS current. So come to letter I. So if this current is going to go in this direction, the current that here we're going to have another current here, which is going to be I2, and here we're going to have I3. So they are always in a circular motion like that. So this one comes in, goes in that direction. This one comes here, goes this direction. This comes like that. Let's just remember it like that. Okay. So now we want to figure out the relationship between these currents. Okay. So if we look at this point, let's call this node point A. Now, if we use KI, if we apply KIL at node A, what are we going to see? We are going to see that we have IR feeding into that node plus I3 feeding into that node minus I1 leaving that node is equal to 0. Okay. Now we want to find the relationship. Now this one becomes our line current, and this one becomes our phase current. All right, so our line currents, you know, it's currents there. That's IR, IY, and IB. Okay. In our phase currents, that's I1, I2, and I3. These are our phase currents. Now, what I'm going to do is we are going to assume, let me write the assumptions. Assumptions. So assumptions are going to be we have a balanced load. Balanced load means that the resistors are the same. That means we are going to have our currents are going to be, our currents will have the same magnitude but at differing phases. We already know they are at differing phases. And we know that what will be leading is IR, and IY will be 120 behind, and IB will be 240 behind. Okay, so that we should always remember. So IR therefore is going to be equal to I1 minus I3. Okay, That is what we have. So these are phasor sums, because these are phasors, guys. Don't take these as what is algebraic sums. These are phasor sums, because the load I put here, remember the reason why I'm putting a load is this load can have an inductor, or it can have a capacitor in it, or a resistor, or combination of the 3 or 2. That's why I called it load. Okay, so it will be a phasor sum. And then we are saying that we already know that if I have a Cartesian coordinate system here, where I want us to look at the currents. I have a Cartesian coordinate system there, and I'm saying that we have IR. Remember we said R is leading here, so IR will be there leading, and we said behind IR is IY, and behind IY is IB, and we say this is 120 degrees, 240 degrees, but this angle here will be a 30 degree. Yeah? Now this is correct. This is supposed to be our phase currents are supposed to be the ones that are supposed to be here. So this is supposed to be in this phase 1. I'm going to have I1 there. Yeah, these are supposed to be our phase currents. Yeah, and then here what do you call this? I2 and I3 here. Okay. Yes. Good. So forgive me for that one. So our phase currents are the ones that we are talking about. We are saying that they are what? They are the same, but they are at different phases. Okay. So now, if I look at this now, and I want to find so here, blah blah blah. So it's fine. Whatever we get, it to be fine. Okay. So with my equation, IR is equal to I1 minus I3. So where is I1? I1 is this one. Where is I3? Is this one. But we have to minus, so therefore I have to put this in this direction. Okay. In that direction. That's a negative. This becomes a negative I3. Yeah? Then what we're going to do now, we're going to say I1 minus plus minus I3. We're going to add these two phasors. So I take this phasor and put it in front of this one. Then I take the other one, I put it in front of that one. So we're adding the two. So here I'm going to get, let me put it in a different color. So these phasors AD, then there we are going to get our line current. So this is our line current, which we'll call IR. Okay. Our line current, which is what? IR. Okay. Now, if we want to know the angle now, if this is 120, that means this angle here is a 30 also. That means, what does that mean? This means that this angle here is 30, right? So we do the algebraic calculation, that derivation, you will see that eventually you can do that. What we did on the delta, you will see that our IR will be equal to, now remember we said our currents have the same magnitude. That means I1 is equal to I3. These are magnitudes. That's why I'm not putting arrows on them. So now if I look at I1, where is it? I1 is here, it's on the vertical axis. Yeah. What is this angle? This angle, if you calculate, I'm going to do it in a different way today. This is a 30 degree, and that one here is also going to be 30 since it's 19. So if I want to get this one, I can basically say I1 cos 30, and then I also say I3 cos 30, and add the two. They'll give us the same answer. They'll give us the answer. So I can basically say I1 onto this guy. Should I use that method? That one will confuse people. Let's just use the normal one we know. So we can just say our IR in the Y. So I remember these are IR. So IR is a Y component here, and it also is a what? An X component there. IRX, yeah, and IRY. Okay, so IRY will be equal to, already we have I1, which is in the Y. So we just write I1. These are now what? It's a magnitude, scalars. It's I1. Then plus, if you take this one, this I3, if you take it's a sign, I3 sign, it goes on to the Y also. So you must add also that one plus I3 sign 30. Since we said I1 and I3 are the same, we can rewrite this to be just I. And since we said also I1 and I3 are called phase quantities, I can write that as what? I phase. And then this is 1 plus a half, which gives us what? 3 over 2. So IRY is equal to 3 over 2 I phase. Then I can go for I R in the X. Now 1 does not have a component in the X because it's in the Y direction. So the only component in the X we have is I3, which is I3 cos. So I3 cos 30. And we also discovered that this will be a root of 3, I think, over 2 of, now I3, we also called it a phase current of I phase. So to find the IR is the line current, is the, by Pythagoras theorem, is the square root. So we are going to do the same thing. The same thing that we did the last time, and then we will discover something that is interesting. Squared plus the square root of 3 to I phase squared. Now if you simplify this one, you should get a root 3 of I phase. That means now IR, remember, is a line current. It's here, it's a line quantity. So that means when you have a delta connected system, your line current is equal to root 3 of the phase current. That is the conclusion. Yeah. All right. Okay. So that's what we see there. Line current is equal to 3 of the phase current. Now, what about the phase voltage? If in the phase and there's the line voltage. If I say this is my line voltage, and then if I say that the voltage between these 2 points is my phase voltage, what do you see? The voltage between these 2 points is the same as the voltage between these 2 points. That means the line voltage is equal to the phase voltage. So it's really simple to pick it out. You don't really have to cram these two. All you need to know is when you have a line current here, when you are going inside here, you must multiply by root 3. Sorry. The line current is the one that is what? Which one is bigger? It's the line current, So the line current is bigger. The line current is bigger than the phase current. So when you're going in here, you should always know that if you want to find the phase current, you divide the line current by √3. Simple. You're just using this equation. So every time its line is equal to the √3 times the phase quantity. But just that when you are in a star is the voltage, okay, and the current is the same. And it's easy to see if you really understand how to go about this. Line current here in a star connected system is the same as the line current is this one, is the same as the phase current, which is this one. So because they are in the same line, and the phase voltage in a delta connected system, you can see that is the same 2 points. So we remember, if we're talking about nodes in ELC, this is the same node, that's the same node. So the voltage between those two nodes is the same. So you don't really have to claim this. You just have to use your knowledge in understanding in this stuff. So what I'm going to do now is I'm going to solve a question with you. The question or two questions. Yes, I'll solve a question or two questions with you. And then the next topic I'll look at is power. Power in what? In three-phase systems. And then probably will be done with that chapter. You also communicate to me the chapters that what you would have covered and the notes that you'd have sent, so that I also know what to give you. All right, so examples. Calculations. So let's say, now this one is the question in use. It's a question in use, so let me just copy the question. Yeah, what should I do? I can bring a new chain. I'll copy the question in use, and the diagram is also in use. Then I'll just do the calculations so that we are faster. We don't waste time in drawing diagrams. Okay, where is our use? Let's look for use. Oops, here we go. That's multiphase systems. Oh, yes. Okay. An example in use. Be that one. So I'm going to have a new share. I'm going to leave the board now. And then I will solve it here on Microsoft. So a new share, Microsoft Word. And let me show it Microsoft Excel. I want Microsoft Word. Yeah, there we are. So this is the question that we have in use. So in a three-phase 4-wire system, the line voltage is 400 volts. So we are told that our line voltage is what? 400 volts. Okay, so here, so the voltage between this line here is 400, and also between this one, and also between that one, as they've shown here. Okay, it's 400 volts. non-inductive loads, and these loads are non-inductive. They have no inductance. And if you look at the powers, the power ratings are in kilowatts, meaning that these are pure resistors. Okay, they are connected between 3 line conductors, and the neutral is fixed as you see here. So the neutral point is this one. So this is a star connected. We have a generator. Our supply is a star. Okay, that means that these now are connected between the neutral and the other node. So it's connected between these 2 points. That's where our loads are connected. So they are also star connected. But I can redraw it so that you guys can really visualize it, so that you see how these things are really looking like. Okay. So let's do this. So we're supposed to find the current in each line. In other words, you're supposed to find the line currents. So our line currents are IR, IY, and IB. Now, one thing you must know is that this is not a balanced load. You should check there. It's not a balanced load. That means, because you can see that the power ratings, they are different. That means the values of the currents are going to be different also. Yeah? It's not a balanced load. Okay. Right, then okay, so let's now start with this. Now I want to redraw this so that you see. What they did is they connected, they have a wire here, and then that neutral wire is the one that is connected to the resistor. So the resistor is connected between the neutral wire and the phase. So this point is point B. So this resistor is actually the load of B. Yeah, and then this one is connected between the neutral wire and this phase here. So if I redraw this, I didn't want to redraw. If I redraw this, I can just to make it look easy to deal with. I can do this. Okay, what I'm going to do is right here. This is a neutral point, right? So I'm going to say at the neutral point here, and this is our point R. Between these 2 points, we are connecting a load. Because look at this load here. It's connected between the neutral, which is here, and R. So I can simply come and put it between the neutral and R, and there is nothing. There is no change there. So that's 10 kilowatt. So there's no difference there. Okay. Then if this is my Y, so between this neutral here, I connect a load between the neutral and the Y. This is my R. This is my Y. So between the neutral and the Y, I connect a load, and the neutral is here, and the Y is so it's this load here, which is 8 kilonewtons. Okay, then here I have B, and also between the B and the neutral point N, I connect a load again, and that load is this 5 kilowatt here. The reason why I read through this is I want you to see that these loads have been connected within the phases. Are we together? I want you to see that the loads have been connected within the phases. All right. That means it becomes very easy for us to do our calculations. So here I'm going to have a phase voltage sorry, this is a phase voltage. I'm going to a V phase here, I'm going to a V phase there, and here I have a V line. Now our V lines are also balanced, eh? So that means our phase voltage is going to be balanced also. Eh? Okay, let's see how it goes. So the first thing we have to do now is calculate, because we want to calculate currents. Yeah, and as you can see, this is a star connected system. My current here, my I phase current that is flowing here. Yeah, the current that flows from here through to this one, to that one, to the line here. Okay, so it's flowing from, this is a line, from the line, let me just follow this current flowing there through that so this line I should have just connected like that. Yeah, so that we don't mess this thing up. Otherwise you think that there's a connection there. It's like they are parallel, but don't really look at it like that. So let's follow this. Follow this. Current is flowing like that, flows like that, flows like that. So it goes there. So it's only here where we have a node where these currents are going to aid each other, right? At the neutral point. Yeah. So we have a line current here that flows also in the same, in this one here, our line current. So that means I have a line current here, which is I. Let me call this I1 here. Okay. And then here I can call it I2. Here I can call it I3. Then our phase currents are going to be IR here, IY here, IB. So for us to know the currents that are flowing, we must know the voltage in those phases. Okay. So this now allows us to start our calculation. So our calculation, we know that line voltage is equal to √3 in a star connected system of the phase voltage. But we are given the line voltage. What we want is the phase voltage, which is VL over √3. Why? Because our appliances or our loads are connected in the phase, across the phases, right? Yes, they are not connected across the lines, they are connected across the phases. That's why we need the phase voltage. Okay, so it's gonna be 400 divided by √3, which will give us 230 volts. Okay, that's the phase voltage. Now, from there, we can now start calculating what? The line currents. Simply because we know that in a star connected system, our line current is equal to the phase currents. All right, so IR will be equal to what? Its power is equal to VI, and these are scalar quantities. You can see that this is purely resistive, so that formula applies. Yeah, this formula applies because it's a pure resistor. Our loads are purely resistive. So I can see that my IR is going to be the power divided by the voltage. Now this is a phase voltage. Okay, so IR, so we say it for R, we are connecting what? 10 kilo. So it's 10 times 10 to the power 3 divided by 230. If we simplify this, we get a 43.5 5 amps. So that's IR. And you can also calculate IY. Still the power in that one, power over V phase, and the power in that line in IY is 8 kilo divided by 230, and that gives us 34.8 amps. And then we have I B is the power in that phase divided by the phase voltage, and that is 5 times 10 to the power 3 divided by 230. This gives us 21.7 amps. So what we have done now, we have calculated what? These are the line currents, and which are also the phase currents. They're the line currents, but they are also the phase currents. Now, what you must always remember is if it's IR, that means this one is the one that is leading. So the angle here, if I'm going to write it as a phasor, yeah, is 0. Remember, each phasor here remains the same because the load is purely what? Resistive. So the phase differences are merely because of how the generation, the electricity is generated. They've already, we have different what their phase angles to the what, to our power sources, our quantities. Okay, so these angles are coming from the source. They are not coming from, they are not being affected by the load. Okay, we don't have power factor things that we're talking about here. So if I write them as phasors, these will be the answers. All right. Now the reason why I'm writing as a phasors is because I want this to help us solve the next question. So the next question is saying calculate the line, the current in the neutral conductor. So in the neutral conductor, you see that currents, these currents are coming at this neutral conductor here. You have this current, it's coming in there, coming in there, coming in there. So all those currents are coming together, then they add up to become the current flowing in the neutral conductor. But when we derive this, remember we say that if the loads are balanced, we said that this current will become 0. But in this case, these loads are not balanced. That means in the neutral line, we will have a current that is valid. We have a value of current. So you can choose to do it in a trigonometric way, where you draw these phases of the currents, then you resolve them in the vertical components, in the y, in the x and the y. Then you come up with you use your Pythagoras theorem to solve it. But you could also use phasor sum. So I can simply say here my IN is going to be equal to my IR plus my IY plus my IB. Okay, so knowing that my IR is 43.5 angle 0, then this one is 34.8 angle negative 120 plus 21.7 angle negative 240. This is my currents. Now if I simplify this, stuff, okay, if you do simplify this, you solve, and then you find, what are you going to find? What are you going to find? What are you going to find? Let me do the calculation. I wanted to ignore it, but I can't. I'm going to find 43.5 minus 17.8 That's 10.8, 17.4. Okay, so you're going, if you solve that, you're going to have 15.25. Okay, then minus J 11.45. Then your IN is a magnitude. Then you change that to polar. Yeah. So to polar form, you do 15.25 gives us a 19. 18.898 depends, né? So I kept this one. 18.98, that was a 19 for me. 19.07 at an angle of negative 36.9. So this is the current flowing in the line, eh? 19.07. So if you just wanted the magnitude of current IN, so this is a phasor. If you wanted IN, you just get what? 19.07, or you can get 18.9 or something there that is close to that one. So that's how you're going to solve this one. But I think I need to re-explain on the diagram that I just drew here. What is important is for you to realize where these things are connected. Okay, that is what is important. See where it is connected. If you don't see where it is connected, you will find it very difficult to do the calculation. Okay, find it very difficult. Yes. So maybe I should just try to restructure the diagram because I don't think this one is really clear. Let me just redraw it again in a nice way. I can draw it here and say that I have my source here. You could draw it like that. You could have drawn it like that, and then okay, this is funny, but it's still fine. Eh? It's now, what is this happening? Okay, here, there, there. Now this is our neutral point N. This point R. It's ugly, but it's correct. Okay, point R. So neutral point A, I'm going to take this line and put it right there. And I say, okay, between that line and R, I'm going to connect this resistor here, which is the 10 kilowatt. Okay, that's our line, our neutral point. And then between, this is B, I'm also going to connect a resistor here, which is the 5 kilonewton. That's point B. Then between this one, I'm also going to connect is the 8 kilonewton. Okay, so this is just as a node. Eh? So now you will see that you have a loop here, right? Where in that loop you have your phase voltage there, and then you have your resistor here and the power that is being consumed there, and you have your current, which is your line current, which is also equal to your phase current there. Okay, so it's like you have three simple circuits. So it's like we've gone to that arrangement where we had something like that. Where now this is our phase current, our phase voltage, and this is our line current, which is also our phase current. And this is our resistor. In this resistor, we have power that is being dissipated there. So the formula P is equal to VI of works there, which will help us to find our current, but this must be phase voltage. So what you needed to understand is that you needed to calculate the phase voltage, because without the phase voltage, you wouldn't be able to calculate this. So it's basically you understanding how this thing is connected and whether you need the phase voltage to calculate or do you need the line voltage to calculate. But mostly, in most cases, we are going to be using the phase voltage to do our calculations. Right, so that is it with the first example. How long has this video been going? I think it is almost an hour. So you could try to look at the example 2 in your book. If you find it difficult, we'll look at it together. Okay, have a good day.